So, hello everyone. As you could probably tell, I'm Georgia. I'm from Imperial College London, and admittedly, this title is a little bit of a misnomer because I have extra slides. If you want to ask me on the toxicology, you can, but it is not in this presentation currently. I'm supervised by Dr. Mark Stetler and also Professor Terry Tetley, and just welcome to my presentation. So to begin, we are going to talk about the overview of my research. As you can tell, there is a little bit of a plane theme that is going on with this report. So we're going to talk about current research and the research objectives of my PhD, but also how this presentation fits into the overall scheme of my PhD. I'm going to talk a bit about my Gatwick sampling campaigns, then some of my results, and also conclusions and future work. So to give you a little bit of background on current research, aviation particulate emissions in terms of combustions have been missed for the longest time. We're starting to see more of an idea of how much of an impact they have in terms of health and also what they characterize and look like. And these studies have led to the International Civil Aviation Authority creating aircraft emission standards regarding NVPN, which Fergus mentioned yesterday. In terms of cytotoxicity and the health impacts of these emissions, we've been traditionally relying on epidemiological data, but also looking at exposure studies in very controlled conditions, also using aircraft NVPN. I'll come back to this point later. It's not as representative as it should be. So what is my PhD project on the whole? The idea of my project on the whole is to create a surrogate source using a burner. But what we're doing with this presentation and how we're combining it in is we're talking about evaluating this burner and then comparing it with real life data by using fieldwork at Gatwick and evaluating particle size, morphology, chemical composition, atmospheric aging, and so on. So a bit about Gatwick Airport. If you didn't already know, it's the second busiest airport in the UK, and it has currently operating at 32.8 million passengers in 2022. It was when this study was conducted. As aware of the pandemic, this is 70.5% of its operational capacity. Gatwick Airport operates on 24 hours, but has restrictions overnight, which limits flight operations and movements. The nearest neighbouring town is Hawley, which has over 27,000 residents. And there are currently plans in place to develop a second runway, which will further increase operational capacity. One of the reasons why this monitoring campaign is important is they are currently undergoing consultations for this runway, and we hope to get in before these are finished. So the idea of where we are, the monitoring station, the monitoring station is here. It's about 1 kilometre away from the runway, which is down here, and it is located in a residential area next to a children's play park and a residence home. So this is directly impacting the residents that are located nearby. How we did this, today I'm specifically going to talk about a winter monitoring campaign. So this was in November to December over 2 weeks, where we sampled using an SNPS, an ELP, a Moody for filter measurements, and also a biosampler that allows us to do some liquid collection analysis. So how we did this and how measurements were conducted, I monitored constantly with the SNPS and the LP. Occasionally, we turned on the catalytic stripper and compared the catalytic strip emissions with those that had directly gone through the SNPS directly. So to give you an idea of some of our results on a number concentration, first of all, just bear in mind there are two different measuring operations that are going on here. So there are differences in number, and also that the LP monitors at a much larger size range, so you should see a much larger number concentration from the LP than the SNPS. Also, in my group, we have seen this difference between LP and SNPS measurements before, so this is something that has come up in our research before. Now, what you can see in our measurements is that we have distinctive periods of very high levels of particle number concentration, and also distinctive changes in the particle size number concentration. Essentially, they're inversely correlated. If this is particularly well highlighted here on this side, where you see as the particle number concentration drops off in the middle of these peaks, particle size jumps massively. So let's add a little bit of data to see what is going on here. If you add in your Gatwick Airport restrictions, which are highlighted in grey, and also wind direction, which is coming from the orientation of the runway in blue, you can see that when the wind is coming off the runway in blue, the particle number concentration increases, what you would kind of expect. Now let's go into a little bit more detail here and talk about how we play with that wind direction and also operational capacity. So wind direction is coming off the runway, which you would assume means particle concentration is high, but actually what we're seeing during those hours of restriction in that grey period, that the number concentration drops off and also the particle size starts to increase again. You also have a lovely perfect storm in this example, where you've got the restrictions are kicking in and the wind is now off them, is not coming from the runway, it's from the local area, and as such, the particle size has jumped quite significantly compared to before. It's also quite comparable to the later parts of the study. So let's give you an idea in terms of the wind direction and focusing this all in. So if we talk about the weather conditions and the particle number concentration, if you think about it, the marker area here is proportional to the particle number concentration. So the larger the marker, the bigger the number concentration. If you put this all in together and put this on a map, what you will see is that wind direction from the runway and larger number particle concentration, and it's quite distinctively a difference. You talk about this in terms of particle size. Again, particle area, the marker area is proportional to particle GMD. What you see is that the smaller particles are coming from the direction of the runway, and arguably, in this case, wind speed, which is the radial axis, is influencing some level of distribution. So again, overlay this on a map, what you're going to see now is that these smaller particles, again, are coming from the direction of Gatwick Airport, and some of these larger particles are coming from the east of this monitoring site here. So it could be coming from the road or could be coming just from the local area. Breaking this down into a little bit more detail and relating this to non-volatile particulate matter, which is what is currently legislated for. We used our catalytic stripper, which is operated at 350 degrees, and I scanned for 10 minutes, essentially, and then compared this immediately to a sample where you turn that off. As you can tell with the standard deviation within our 10 scans of the sample, particle emissions at Gatwick are incredibly changeable. It's not constant, it is very much fluctuating. But if you can see, the airport non-VPN is much higher than the local airport non-VPN, and the particle diameters are completely different. Now, why is studying volatiles important when considering toxicology? Well, if I add in the volatiles, this is what happens. You're seeing this massive decrease between our volatile total component here and the non-volatile component here. This entire set of particles are missed out when we are not accounting for volatile particulate matter. In fact, if you consider the volatile to non-volatile particulate matter ratio, when the volatiles are coming off the airport, you're considering around 70 to 90% of particle number is coming from volatiles. Whereas if you're from the local area, that's between 50 at a maximum and between, nothing. So it is a massive contributor and is something that needs to be considered when we look at our emissions. So again, comparing this emissions by source, if you take a lot of the scans that are put in, again, standard deviation, Gatwick is not stable in terms of this. You'll see local source down here, very much in a large group. And then if you move your airport, you can see a much larger total non-VPN and also much larger total PN counts. So conclusions and further work. The one thing I want you to take away from this is large numbers of small particles originate from Gatwick Airport, which is what we would expect. But also the particle size is negatively correlated to particle number concentration, which is also useful. And again, that this volatile PM, which we're currently ignoring, is making up a huge contribution of airport emissions compared to local emissions. So in further work, which is currently, there is results for this, but it won't fit in this presentation. We're doing the toxicology for the samples collected from the summer and winter campaigns, and some of this is still ongoing. We want to relate these results to the surrogate source produced by an inverse diffusion flame burner. So essentially saying, are our distributions the same and how are we going? And then finally, we want to work on the toxicology of the emissions of SAF fuels or 100% SAF fuels and compare that to traditional combustion engines and see if there's any change. Thank you, and any questions?